All right, so this week's lab is going to be on collisions. Before we go over collisions, since this stuff may not have been covered in the main class already, I'm just briefly going to define momentum and energy. Momentum and energy are very useful quantities that are used for solving a lot of physics problems, but we'll need them today to look at collisions. So momentum is a vector quantity, and it's just equal to mass times the velocity, which is also a vector. Now, in today's lab, or in this week's lab, everything will be in one dimension, and so you don't really need to worry about the fact that it is a vector, but it is a vector in general, and in problems where there's more than one dimension, you need to, be careful about that. The other quantity we'll be using is kinetic energy. So kinetic energy, I'll call K, is equal to 1/2 mv squared, or p squared over 2m. And so in collisions, momentum is always conserved no matter what type of collision we have. Kinetic energy is not always conserved. So total energy is always conserved, but in any physical process, you can have energy converted to heat or sound or vibration or other forms that do not contribute to the kinetic energy that you're looking at. So we'll be looking at well, there are two main types of collisions. There's elastic collisions, which are collisions where kinetic energy is conserved. So like I said, in general, if you call the initial momentum just P and the final momentum, or I guess we'll write Pi and Pf for initial and final. In all collisions, the initial momentum should equal the final momentum. But in elastic collisions, we should also have that the initial kinetic energy equals the final kinetic energy. So other than elastic collisions, there are also inelastic collisions. And in inelastic collisions, and also, I'll do my best to speak clearly, but it does get a little bit confusing because, in an elastic collision versus in an inelastic collision, it's easy to confuse things when they're said like that. But so in an inelastic collision, energy is converted to other forms. So that in general makes problems involving inelastic collisions more difficult to solve, but we'll be looking at a special case, which is a completely or totally or perfectly inelastic collision. And that is where two objects stick together after colliding and move as one. And that gives you kind of an extra mathematical equation that helps you solve those type of problems. For a general inelastic collision, you need to know how much energy is lost or some factor like that. Sometimes you could use an elasticity factor, which would be what percentage of the energy is conserved in that type of collision. But we won't be going into those in today's lab. So I'll just write inelastic and K initial not equal K final. So now I guess I'll go over the elastic collision that we'll be covering in today's lab. So we're going to have a track with two carts on it, and we're going to have one of them initially at rest. We're going to push the other one into that cart, and then we're going to look at what happens. So drawing that situation, we have first part with M1 and V1. And then we have M2 and V2 we'll say is equal to 0. And we want to know what happens after these carts collide. So the first collisions we'll be looking at are elastic collisions. I meant to give some examples. In the real world, billiard balls are very close to elastic collisions. In reality, all macroscopic large objects will have some amount of energy converted to heat or something else. But there are certain things that are pretty well approximated by elastic collisions. Atomic and subatomic interactions a lot of times are elastic. If you shoot, two electrons at each other, if it's high enough energy, it will become inelastic. But at low energies, that is an elastic collision that you'll get, or any charged particles that you shoot at each other.